Hi everyone, today I'm working through question 13 part D of the 2020 Extension 1 trial exam from James Ruse. So it's a two-part question, so as usual I'll work through each part in a separate video, and in this video I'm focusing on part 1. The background to the question is that Danny wants to swim across the river from position A to position B as shown on this diagram below. The riverbanks are parallel straight lines and the vector AB is perpendicular to the riverbanks. We're told that the speed of the river flow is 30 meters per minute from west to east, and the river is 240 meters wide. And then we're told to assume that Danny can swim at a constant speed of 60 meters per minute. So we've got the diagram here, and we've got north as being pointing up for this diagram. And part 1, which we're going to focus on here, is in which direction should Danny aim to swim in order to move from point A to point B in a straight line under the influence of the current? And we're told to draw a vector diagram to demonstrate the velocities and show all necessary working out. So let's take a look. So here's my diagram that I've recreated. We've got our parallel banks of the river, and we've got this vector AB, which is perpendicular to those riverbanks, and it spans a distance of 240 meters. We've got north as pointing up, and where the two key pieces of information are that the river is flowing from west to east, so in this direction, at a speed of 30 meters per minute. And we're told that Danny, who I'm just going to call D for the purposes of my working out, D can swim at 60 meters per minute. So our question is, in what direction should D swim to get from A to B? And I think the first point to note is that D can't just swim straight up. If D swam directly north, then the river flow would start to push him towards the east. So we actually know that as a starting point, Danny, D, needs to effectively, he can't go straight up because the river will push him east. He can't go northeast because he'll get pushed even further east. So we know we're thinking of some direction in the northwest direction, so that whatever direction we go, the river kind of pushes us so that effectively we end up just coming straight up from A to B. That's the basic idea. Obviously we're not going south because the river B is north of A. So our options are either north, northeast or northwest, and hopefully it's obvious that it's got to be some angle northwest because the river is flowing from west to east. So what I might do is I'll just draw onto this diagram a vector coming out from point A and hitting the other side of the river, and maybe I'll just call this point X. And I think the basic idea is that if Danny's going to swim from point A to point X in that direction, and effectively the river flow is going to push us from point X to point B, then what we can say in vector notation is that we're effectively, to get from A to B in terms of a vector, we can get there by going from vector AX plus vector XB. That's basically what we're doing. And as usual, you can cover up the middle bits and you can see the vector AB is vector AB there. So we will end up going from A to B just in this fashion, swimming in this direction with the river pushing us at the same time. That's the idea. And so ultimately the question, because we're being asked what direction should D swim, effectively it's north, west, where the kind of the extent to which we're going west we could describe as being this angle here, which I'll just call alpha. So it's angle BAX, which I'm going to call alpha for working out. So that effectively our answer will be, north, alpha, west, in terms of almost like a bearing is essentially how we're going to answer this question. So given we're told that this AB is perpendicular to the riverbanks, then we also know that this will be a right angle too. So we've effectively got a right-angled triangle that we're dealing with, and this can almost reduce to a trigonometry question, because if we want to find this angle alpha so that we can state our direction as a bearing, if we can find, say, this opposite and this hypotenuse, then we can use the sine of alpha and you know, get the inverse, and we'll have alpha isolated. So that's a sensible way to go. And I think to get there, what we can do is, first of all, we can assume that for D to get from A to B in this fashion, he needs to assume that Danny, D, needs to swim for, let's call it T minutes. Now, we don't necessarily know how many minutes T is, and it almost won't matter. As we'll see when we do our working, it really won't matter what that T happens to be. But it's useful to just define it so that we can start to think of essentially our speed as being distance over time. So if D needs to swim for T minutes to do what he's got to do, then effectively, because we know he swims at 60 meters per minute, we can say that 60 would be equal to this distance here that is effectively got to swim at this angle, which is the magnitude of AX vector divided by time, that T, that T minutes. That magnitude divided by T, we know will be 60 because that's the speed at which D swims. And so with a simple rearranging, we can therefore say that this distance, the magnitude of AX vector, will be equal to 60T. So I can just multiply the T up. So this length here is effectively 60T. And using a similar idea, since the river is flowing from west to east in this direction here, the same direction as going from X to B, we can know that 30 will be equal to the magnitude of the vector xb divided by t. So same idea, to get from here to here in t minutes, that speed is 30 because that's the speed at which the river flows. So again, simple rearrangement will give us the magnitude of xb vector will be equal to 30t, so that this length is 30t. And then, as I mentioned, now since we're really concerned about this alpha, we can use sine of alpha will be opposite on hypotenuse. So we can say, therefore, maybe I'll just say from triangle ABX, we can say that the sine of alpha is equal to the opposite over the hypotenuse, so 30t over 60t, and these t's cancel, and this 30 on 60 will reduce to a half, and so really alpha is equal to the inverse sine of a half, which if you know your triangles, you probably know off by heart, but it's always helpful to make sure. So I'll just use my calculator and we'll go the inverse sine of a half, and that gives us our 30 degrees. And so therefore we can conclude that D should swim, basically we'll say north 30 degrees west. So north 30 degrees west, and I reckon that would do it for this question. It was just a 1 mark question, so actually I think that's probably pretty fair. Maybe it might have been nicer to be a 2 mark question, one for kind of working out what you got to do and then another mark for doing it. But yeah, you shouldn't expect to have to do too much work for this 1 mark question. Hopefully that kind of makes sense in terms of a broad approach. I think the key to this question was, first of all, just thinking almost logically about you know, your options for Danny to swim and kind of thinking, well, it can't just be north because the river's going to push me east. It can't be northeast because I'm going to go too far east even more than if I was just going north. So it's got to be some direction northwest. And then from there, it's almost trigonometry at that point, a bit of trigonometry and a bit of bearings in terms of how we state it, and you're basically done with that question. So hopefully that's made sense, and you could follow along with these steps. And what I'll do in the next video is I'll focus on part 2, which pretty much follows on from this. It's kind of similar ideas, just a few more techniques that we need to make use of. So yeah, there you have it. Tick boom.